the punchline is about new paths, or new path, I should say today, to proving upper bounds on the exponent of matrix multiplication. And I'll remind you what that is if you weren't, or tell you what it is if you were not here this morning. Is there anyone here who was not here this morning? Okay, good or bad. Okay, so anyway, I'll remind all the definitions anyway. So preliminaries. So I apologize because there's going to be a lot of definitions. We need the definitions from computer science. We also need the definitions from algebraic geometry. So it's kind of way down the talk a little with definitions. So I'll try to explain as I go along. So A, B, and C will be finite dimensional vector spaces over the complex numbers. Everything in this talk is over the complex numbers. Usually they'll have the same dimension. And T will be a tensor. And i.e. a bilinear map from, say, A dual plus B dual to C. But I prefer to think of it all three vector spaces on the same footing. And then we had this definition from this morning, the border rank of T. Well, this is the smallest R such that T is a sum of R rank 1 tensors, or a limit of such, i.e. The smallest R such that T is in the rth secant variety of the Segre variety. So hopefully either one or the other of these definitions makes sense to you. And all this stuff is motivated by one particular tensor. So this will be a Cn squared, tensor Cn squared, tensor Cn squared, where I really should think of this as the space of n by n matrices, etc. This is the matrix multiplication tensor. So as a bilinear map, it eats two matrices and spits out their matrix product. And this exponent of matrix multiplication is defined v the inf over tau, such that the border rank of this particular tensor grows like n to the tau. And so classically, omega is less than or equal to 3. And the astounding conjecture is that omega equals 2. That is to say that you can asymptotically, as your matrices get bigger, you can multiply them almost as easy as you can add them together. And the state of the art is omega is less than, well, let me just write 2.38 or so. A little less than that. And, oh, but I need to say the state of the art via something called Strawson's laser method. And this laser method, I'm going to explain the essence of it to you, but it's very bizarre. It's a mixture of probability and combinatorics and allegedly statistical mechanics. Now, I say allegedly because Strawson says his calculations were inspired by statistical mechanics, but since I don't know any statistical mechanics and you formally don't need to know it to understand the laser method, we'll just leave it at that. But certainly that involves probability and combinatorics. And what I want to do is approach this laser method not via probability and combinatorics, but via algebraic geometry and representation theory. So that's the goal. And now I need a bunch more definitions. So if I have two tensors in different spaces, or maybe in the same space, I don't care, you have something called the Kronecker product. And this is the tensor product of these two tensors, but I'm going to reorder and think of it as a three-way tensor. And it's easy exercise that the border rank of the Kronecker product is less or equal to the product of the border ranks. And what is interesting is that strict inequality is possible, and that strict inequality somehow is driving a lot of the discussion with regards to upper bounds on the exponent. Similarly, we could define the kth Kronecker power of T. So this will sit inside A tensor to the K, tensor B tensor to the K, tensor C tensor to the K. And yet another definition. Let's say S and T are in the same tensor space. We say T degenerates to S, and we write it like that if S is in the orbit closure of T. So if I didn't have this bar over, I would just be getting the different ways of presenting T in different choices of coordinates. But what's interesting is what happens on the boundary. So now I could tell you the idea of the laser method. So find T of small order rank, say R, and K, such that the kth Kronecker power of T degenerates to a matrix multiplication tensor with n large, as then get that the border rank of matrix multiplication is bounded above by R to the K. Now, the amazing thing about this is it actually works. I mean, it's a kind of, as far as I can tell, it's a ridiculous idea. And a key part of that is due to is a theorem that preceded it due to Schoenhagen, which hinted that such a thing might actually work. So I'm going to tell you the best tensor so far. So this is all upper bounds since 1988 use this tensor. And it's got its own name, the big Coppersmith-Winograd tensor. There's also a small one, but that one won't play a role in today's talk. And it comes in a family. For each Q, we get one. I'm using computer scientist notation. So we'll sum over J equals 1 to Q of A0 tensor Bj tensor Cj, where these are all basis vectors. And their respective spaces. So you'll notice that this tensor is actually can be presented as a symmetric tensor. It is. And there's also, it's worth noting there's a special case, Q equals 0. And this one has a name in the quantum information theory literature. It's called the W state. But to an algebraic geometer, this last three terms is just a general tangent vector to the Segre variety. So I know that was a lot of definitions, so maybe you have any questions about all these definitions? Yeah, like I said, it was combinatorics. So they were looking for a tensor with certain combinatorial properties. If you want me to be precise, if you just look at this piece alone, this looks like a matrix multiplication tensor, a 1QQ matrix multiplication tensor, and so do these. And in fact, there was the little Coppersmith-Winograd tensor, which was just this, and that one was giving the state of the art. And then they said, oh, at no extra cost, we can add this additional term to maybe get more juice. And so that's, it was, I would say, ad hoc. I still, unfortunately, need a few more definitions. Tensor is concise if it can't be put in a smaller space. More precisely, we could also consider a tensor as a linear map from the dual of A to the space of matrices, and that this map is injective. And same for TB and TC, also injective. So okay, yeah, I guess we're not going to see that board anymore. I can push this one up. So if T is in CM tensor, CM tensor, CM, and concise, it's easy to see that the border rank of T is at least M. And if equal, we'll say T has minimal border rank. So for example, this CWQ has minimal border rank. And then in 2014, so in 2014, yeah, so let me write the names down. Benus, Mas, and Legal. So this Legal, and in 2014, proved two theorems. One is he became the world record holder for the upper bound on matrix multiplication exponent in that year. But a sign of a good mathematician, he also proved game almost over for this tensor. And that is more precisely, can't prove omega less than 2.3 using the standard laser method and this Coppersmith Ringard tensor. Questions? So unfortunately, I don't understand this proof, but fortunately, a few years later, a geometric theorem was proven that I do understand that I'll share with you in a few minutes. So, but this naturally leads to two ideas to go further. One is improve the method. And the best idea that I'm aware of, someone in the room, and Yelishev. So if I just write the initial, that means it's one of those names over there. They've made the most interesting progress on that by taking advantage of some local algebra. And then the more sort of naive idea, find a better tensor. And today's talk I'm going to present a provably better tensor, but the caveat is so far no new bound. So I have to say, how could I be sure it's better if I don't have a better bound? And hopefully I'll convince you of that. So so find a better tensor. What?
Have you told us how you're proving that S is in the orbit closure of T in these cases? So
no. Oh, it's a definition.
Sure, but when I use take your Kronecker power, still have to prove that there's the orbit closure with the matrix multiplication.
That's correct. And that's where this probability in statistics comes in. In fact, I don't know. So one of the things I've learned, I've learned all kinds of stuff working in this business, and one of them is this so-called probabilistic method. So they take this high power, and then they want to prove that some projection of it has the property they want. And they prove a random projection of it does, although they cannot write an explicit one down necessarily. And that's done by some general counting arguments and stuff. But it's a fairly delicate combinatorial argument that I'm not going to go into, and I should not try because I would not succeed in conveying it correctly. But I understand the argument, but I would not be the person to do so. So yeah, so the main debt, main beautiful piece of chalk. The main debt will be to explain the meaning of that word, because otherwise this thing is like a vacuous talk. So let's see. So in 2019, Kirstendahl, Brana, and Sweetum did a geometric version of this Ambénis Filmus Legal barrier. And this, I will explain to you, it's a very clean explanation of why game is almost over for that tensor. Although I won't reproduce the calculation that proves it, I will give you something that you can clearly measure to prove it. Okay? So, yeah, so I'll need yet a few more definitions. These go back to Strawson. So there's this asymptotic rank. So these three guys are in quantum information theory. And a lot of the ideas in the laser method have a very heavy overlap with the ideas of quantum information theory. So it's very natural that these folks would be proving good results about laser methods. So there's this asymptotic rank Strawson defined, R tilde of t, which is the limit as k goes to infinity of the border rank of this Kronecker power of t. But then we have to normalize it to the 1 over k. And you should think of this as cost of your tensor. And recall, so notice that this border rank of t can also be defined as the smallest r such that this unit tensor degenerates to t. So this is just r copies of the 1-by-1 matrix multiplication tensor. This is, M1 is just a rank 1 tensor. And then you could define going in the other direction, qt, so this is the border subrank. This is the largest r such that t degenerates to a unit tensor. And then there's the asymptotic subrank. And this is defined to be equal to the limit as k goes to infinity of this q bar of t Kronecker k 1 over k. And this you should think of as the value of our tensor. And of course, we have that q tilde of t is greater than or equal to q bar of t, and r tilde of t is less than or equal to r of t. And their theorem is that the ratio, well, they took ratio of logs, but I don't care. This quantifies the barrier, this AFL barrier. In particular, so this is always less or equal to 1, always. And if strictly less than 1, T cannot be used to prove omega is 2 in laser method. So they call this the irreversibility, or the logs of these. So now, you see, even for this problem, there's 2 strategies. Just like if you're running a business, there's 2 ways you can improve your business, right? You could either lower cost or increase profits, right? So that's the 2 strategies, right? So look for higher value tensors and CWQ, even if the initial cost, i.e. the border rank, is greater, and hope that you win asymptotically. And that's not what I want to talk about in this lecture. I want to talk about the other option. But for those of you who remember this morning's lecture, I talked about 2 tensors, the 3x3 permanent and the 3x3 determinant considered as tensors. And I said it was very important to computer scientists to determine those border ranks, because the 3x3 permanent tensor is one of the few tensors that could potentially prove the exponent is 2. And our result, unfortunately for them, was a lower bound. So we gave negative evidence for the utility of that tensor. So that was a question open since 1988. The other one is more interesting because that one was very good news, because the 3x3 determinant also has the property that it could potentially prove the exponent is 2. And it is the Kronecker square of just the unique skew symmetric tensor in C3, C3, C3. And that one, there's a dramatic drop in border rank under Kronecker square. So that one was very hopeful news for this laser method. But unfortunately, computing the cube is a little too difficult for us at this moment. So instead today, I'm going to talk about find minimal border rank tensors. So if they have minimal border rank, they have minimal asymptotic rank of higher value, higher asymptotic subrank than this CWQ. And this is what I'm going to talk about. And the interesting thing is, of course, not, it's one of these things, if you don't have fun along the way, you're not going to have fun when you get there. The really interesting thing is how we're going to get there, which is a beautiful story. So let me try to convey that story. But before that, I just want to shift gears and talk about geometry for a minute, because, well, I said I was going to. So let's let G be a reductive group. For example, GLN, or a product of such. That's the one that's most important today. And V, an irreducible G module. V, a point in projective space. And we define the stabilizer of V and a classical theorem, mostly Matsushima, if GV is also reductive, then the boundary of the orbit closure of V has pure codimension 1. So that is to say, the boundary may be a union of a whole bunch of different varieties, but each of those varieties has codimension exactly 1. And the case we're going to talk about today is turns out the tensors of minimal border rank, that variety of at most minimal border rank, so these are all, this is so the stabilizer of that line is a torus, so in particular it's reductive. And this orbit closure is exactly the set of tensors of border rank less than or equal to m. And if we intersect with concise, then this is border rank equals m by what I said. And these are the minimal border rank tensors. So that's our hunting ground. Well, the orbit itself is useless because that's just a tensor we know already. We want to know what are the interesting things, and we want to know interesting things that should have high asymptotic rank. And if you think about what that means, we want it to be close to the interior. And there's going to be another condition that I'm going to add for goodness in a minute. So, yeah, so previous theorem, Yelishev, myself, and my student Arpan Pal, when m is less than or equal to 5, the boundary, let me call the boundary in this case, I'll use the notation sigma, boundary sigma m. Then the boundary of sigma m intersect concise is the orbit closure of this tensor 2 sizes down plus the quantum people's favorite tensor w, the tangent vector to the Segre. Now, in other words, this is the thing that's closest to the interior, and everything else is further away from the interior. Now, this, from the point of view of the laser method, is a little disappointing because the laser method does not work well on this tensor. If you wanted to use this tensor in the laser method, that's equivalent to proving upper bounds on the border, the matrix multiplication tensor directly, and that is above the pay grade of everyone working on the problem at this moment. The technology does not exist. The idea is to work indirectly. So we want something that looks very different from this that still does the job for us. So it also says that, well, this is kind of interesting because, first of all, there's only one component of the boundary other than the trivial stuff. And second of all, that component is itself an orbit closure. W is a general tangent vector to the Segre variety. It's the CW0 tensor. Anyway, yeah, I'll write it again. It's A1, B1, C1, C2 plus A1, B2, C1 plus A2, B1, C1 with the tensor product signs. It's what you get literally if you take a general tangent vector to the set of rank 1 tensors. Right, so what about larger M? And this is the theorem. For M greater than or equal to 16, there exists other components of the boundary, and with qualitatively different geometry. In particular, they won't be orbit closures. So that's the theorem. Any questions? Okay, so I think this is my last definition. Yeah, this is my last tensor definition of the talk, so I apologize. So many definitions today. T is 1A generic if, when I look at the image inside the space of matrices, if it's not contained in the degeneracy locus of determinant 0. And it's 1 star generic if 1A, at least one of 1A, 1B, 1C generic. It's binding if at least 2, and it's 1 generic if all 3. And this CWQ is 1 generic. So it's a very natural genericity condition. A few years back, Emanuele, not that many years, that would be a few years forward, I guess. Austin, Connor, Gesmundo, myself, and Emanuele Ventura, who is still here and still awake, among minimal border rank 1 generic tensors, none is worse than this big Coppersmith-Winograd tensor for the laser method, i.e. T minimal border rank and 1 generic, then T degenerates to this Coppersmith-Winograd tensor in the appropriate space. And this says I could just start with T, degenerate it here, it doesn't cost me anything, and then pretend I had Coppersmith-Winograd. So it has to be at least as good, but we did not prove that anything was better. And now I'm going to shift gears. And the rest of the talk is going to be about something called Gorenstein algebras. But before I do that, notice that this tensor is the structure tensor for the algebra of matrices. That is to say that matrix multiplication is multiplication in the algebra of matrices, and any algebra, we get T sub A, its structure tensor. And proposition Laser and Lysakov, if T is binding, then T is the structure tensor of some algebra with unit. And a corollary of Strawson, after you have this theorem, says that if T is binding and minimal border rank, then this algebra is also associative and commutative. And in fact, in hindsight, that's really how Strawson got his lower bounds by exploiting commutivity. He didn't even bother to deal with associativity, but that also seems to be a non-trivial condition. Now, for the experts, if T is one generic and minimal border rank, then in fact this algebra is even Gorenstein. And you don't even know what a Gorenstein algebra is. I'm going to basically tell you what all of them are. So there's an important class of finite dimensional algebras that I'm going to describe, and this will be the Gorenstein. So let's let V be a vector space and let P be a homogeneous polynomial. Degree D. And we consider the annihilator of P inside the dual algebra. So these are just phi in sim V such that phi acting on P is 0. So here, of course, I have a pairing of V with V star. That's what it means to be dual vector space. And I have a pairing that's a contraction operator or differentiation operator. So note, this contains sim delta of V for all delta greater than D, because if you differentiate a polynomial of degree D more than D times, you get 0. And so that means that if I consider the question? If I consider the quotient, this is finite dimensional. And also the grading still is there, so it's finite dimensional and graded. So for example, D equals 3 and sufficiently generic, the grading is 1 and 1 in degree 0, 1, 2, 3. And if it's, say, 4 in generic, it'll be 1 and n plus 1 choose 2 and 1, and you get the pattern from there. Just binomial coefficients. And so this structure tensor is of minimal border rank if and only if this algebra is smoothable. And here I mean smoothable in the Hilbert scheme. So if I have a point in the Hilbert scheme, there's this principal component that consists of the trivial algebra of whatever size, which is just a bunch of direct sum copies of complex numbers. And if I can degenerate that to my algebra, I call my algebra smoothable. And a theorem of Yelyshev and maybe some other people, which I won't write down their names because I forget, if D equals 3 and N equals 7, all the above are smoothable. And proposition m equals 16, so n equals 7. D equals 3. We get a new component of d sigma 16. And we actually have two proofs, both of which are informative. We can count, we know the number of homogeneous polynomials of degree 3 and 7 variables up to isomorphism. And if we could prove that the dimension of the associated space of tensors, if those tensors had the correct dimensional stabilizer, that would give us a dimension count that shows it gives a component of the boundary. That's one proof. That's the lowbrow proof that I understand. And then there's a much more subtle proof that says that these things are smoothable, but they're not cleavable without smoothing them. So in other words, that you can't partially smooth the algebra without completely smoothing it to be a direct sum of trivial. And so that's the other proof, which is a little more subtle and interesting. And a bonus, anytime d equals 3, we have an explicit normal form. And I'm not going to waste word space with that because I'm almost done. Already, n equals 3, so m equals 8. We have a tensor explicit T that looks like this CW6 plus, well, I'll tell you what it is, XYZ, but this has a name in the literature. The small is a small CW2. And this has higher Q tilde than CW6. So that is, so let me see if I've paid my debts. So the fact that the cost is the same, but its Q tilde is strictly larger, and that it degenerates to this thing says that it must be better in the laser method than this CW6 because it has, but to actually implement this is quite subtle because you need to take a high enough Kronecker power that the inclusion of this extra term is actually giving you some profit and without killing it. And that step we're working with the experts, you know, Allman and Vasilevska-Williams, who hold the current world record for the upper bound. They see the tensor, they agree with me that it should do better, and we're very hopeful that they will actually make it do better. And I think I've paid all my debts, but if not, you may ask me questions about it now. Thanks for your attention. Well, you see, because if I write CW like Mateusz likes it as a space of matrices, it looks something like this. It looks like there's stuff here, 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 and you have zeros elsewhere. And then what we can do in this d equals 3 situation is we could fill in at no cost, at least when n is less than or equal to 7, but not 6, we could put whatever we want in that pink square, as long as it's a symmetric tensor. It's the image of a symmetric tensor. Now, this symmetric tensor has higher cost than minimal. This lives in C3, 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 but it has cost, that is to say, border rank 4. And we're getting it at no cost whatsoever, this pink thing. But you see, these things, we want to separate them, but they're living in, these things are overlapping a little bit. And the idea is that when you take this high Kronecker power, most of the time they'll overlap, but there'll be some parts where the overlap kind of goes away, or you can make it go away without paying too heavy of a price. And so you need to be able to do that and then still take advantage of the full force of this very useful tensor for the laser method. So it's quite subtle and involves techniques that I do not completely understand. I mean, I understand the idea, but I am not the kind of person who knows how to implement them. Mateusz does a little bit.
So let's thank JM. Question? I have a very important question. So by higher, you mean like you really can prove it strictly higher?
Yes, because this is one of the few tensors where the asymptotic rank is known exactly. And there's good techniques for lower bounding the asymptotic subrank. And those techniques give us a lower bound that's higher than that number. So it's really strictly less obstructed in the, it has strictly weaker barrier than Coppersmith-Vinograd.